So Hubble looked at the redshift of starlight and he plotted the graph that basically showed that if you look at the recessional velocity of a galaxy and you looked at the distance away, there is a link between how far things were away and their velocity. And this graph here has the gradient of h0, which is Hubble's constant. And what we can say is that the velocity over the distance away is equal to the Hubble's constant. You know, that's why it is what it is. And we can therefore say that the velocity is approximately equal to h0 times d, and that's the distance of the receding galaxies. So not just stars in our sort of in our solar system, not just the stars in our galaxy in the Milky Way, but we're really looking at how other galaxies are moving away from our own. Now the thing is that the value of this constant has a value which is approximately equal to about 68 kilometers per second per megaparsec. The reason is that we measure the velocity often in kilometers per second and distances in megaparsecs. But that doesn't really tell us a huge amount. But what we can say is if we have a uniform expansion of the universe, effectively if you have maybe this is the Earth over here, and we have another galaxy a long way away, perhaps a distance of d away, and it's now moving at velocity v, assume that it's always been moving at this velocity, what we can then look at is the time that it's taken to get from here to here. Now this time here is equal to the distance over the velocity, and if we assume that we've got this kind of a finite age to the universe and we've got a Big Bang, the time to go from where these two things were at the same place to where they are now is going to be equal to the age of the universe. But we know that v over d is equal to h0, but here we've got d over v. And what we can therefore say is that the time here is equal to 1 over the Hubble's constant. And this time here is the age of the universe. So if we know the Hubble's constant, we can actually work out how long it has been since the Big Bang. The problem is that Hubble's constant is given in the units of a distance per second per distance. So what we can then do is we can convert this into the SI units of seconds to the -1. So basically, in order to convert this from this unit over here, the first thing we need to do is we need to multiply by 1,000. And if we do that, we then get Hubble's constant as 68,000 meters per second per megaparsec. What we can then do is convert from megaparsecs into meters. And what you need to remember is that basically we're going to divide this, and you need to remember that a parsec is 3.1 times 10 to the 16 meters. But we've got a megaparsec, so we're going to say that's times 10 to the 6. And if we then take 68,000, we divide it by 3.1 times 10 to the 22, we then come up with a value which is equal to approximately 2.2 times 10 to the -18 seconds to the -1. Okay, my number on my calculator is a bit bigger than this, but I've just kept it to two significant figures at the moment. So this is Hubble's constant approximately in seconds to the -1. So to find the age of the universe, we do 1 over Hubble's constant, which equals 1 over 2.2 times 10 to the -18. And we're dividing by a very small number, so then this gives us a very big number. And the answer in this case is about 4.6 times 10 to the 17 seconds. So that's the age of the universe in seconds, but we often want to maybe give this in years to actually kind of make it a bit more meaningful. So to convert from seconds to years, we just divide by the number of seconds in a year, which is 365 times 24 times 60 times 60. And if we do that, we can convert this from seconds to years, and it's equal to 1.4 times 10 to the 10 years. Now I can also write that as 14 times 10 to the 9 years, and that's often a more useful way of thinking about it, because what we then have is an age of the universe of about 14 billion years, and that's kind of what we assume at the moment. Now again, this is based on the fact that we've had this kind of linear expansion and things have always been moving at the same velocity away, which isn't necessarily true. But basically this is how to convert Hubble's constant from kilometers per second per megaparsec into the SI units of seconds to the -1. If we take the reciprocal of that, that then gives us the age of the universe, which is often about 14 billion years old. Thank you.